Okay, so I hope you guys enjoyed the lunch. So we will begin our second session with Joan Bruna, I pronounce it right? Good. Who is currently an assistant professor at the Courant Institute for Mathematical Sciences, NYU. Previously, he has a long list of research positions he had. Most notably, he did his PhD in l'École Polytechnique in France, and then was a postdoctoral researcher both at the Courant Institute and then at Facebook AI Research. And in 2018, he got the Alfred Sloan Research Fellowship. And today he's going to talk to us about optimization landscape of neural networks. So thanks for
Thank
coming.
you. Okay. Yeah, thank you. Hello, everyone, and thanks to the organizers for inviting me. Very nice. I hope I can make it back to New York despite the storm. Anyway, so I'm going to be talking about some work that I have been doing with some of my collaborators. So most of them, so Daniel Freeman, a PhD student at Berkeley, and then Luca Venturi, a PhD student, and Alfonso Bandera, my colleague at NYU. Okay, so as a way to motivate this problem, so we take like the starting point is a bit the same as some of the things we heard this morning from Sanjeev. So the goal of the game is that we have a, that's like the starting point of many machine learning setups. Supervised learning is that we have some data distribution, X thing about the thing you observe, Y is the labels, and then there are two ways where we want to do things. So we have some task that is measured through this through some loss, and we want to be able to predict this target with some model phi. And so there are two ways in which we can evaluate how well we do. One is evaluate it on the data distribution, right? On the training distribution. That's what we typically call the empirical loss. And the other one, that is the one we really care about, that is how well this model generalizes on the population. And so there's this fundamental theorem of machine learning, as my friend Ben Breck likes to say, that essentially tells us how these two quantities, one possible way where one can compare these two quantities. One is saying that, well, how well are we going to generalize at test time? You can think this error, you can think about this risk as containing two sources of error. One is how well this set of parameters, theta star, does on the training set based on the empirical distribution, and what is the gap, what is the distance between this quantity that is random and this quantity that is an expectation value. And so there's a lot of history, and actually also including a lot of recent ongoing efforts in trying to essentially control this generalization gap. This is more like statistical problem, right? You need to understand how to control these statistical fluctuations, and as you know also is that this this is a problem that contains, it's like an aggregate of many disciplines, right? And there's no, I mean, one of the things that we learned from like this seminal paper by Léon Boutou and Olivier Bousquet is that you should not try to take these quantities, you should not try to study these problems independently, right? So how we optimize this model, so how can we make these things small, should not be treated independently as how can you control this thing. But now in the case where that maybe is closer to what we care about when we consider our model to be, let's say, a complicated, large, deep neural network. In a sense, there's only like the things that work in practice, like the empirical practice on how people control this generalization gap, has essentially there are two mechanisms that empirically seem to be very efficient, right? One is to rely on what we call this stochastic optimization, so this like stochastic gradient descent. And the reasons for that are somehow motivated by the fact that the sampling noise that the stochastic gradient descent is, in a sense, has the same flavor as the kind of discrepancy between the empirical and the population loss. And then the other thing that makes a big difference in practice is already of course to incorporate whatever inductive biases you have about the problem into the model. So that's in the case of computer vision, this means making the model convolutional. But also, and perhaps more surprisingly, to make it very large, right? To put a lot of parameters in there. And there's as Sanjeev also mentioned, there's this nice experimental paper that really showed that, to what extent this thing about making the model large is important in practice. So today in this talk, we really care, we try to understand the first question, right? So first thing is how, in a sense, how can we quantify how over-parameterization of the model affects our ability to optimize? In other words, just try to focus on make the energy small. And so what we try to do is we have, essentially, we'll talk about two stories. One is, well, what can we say about these landscapes for both like the population and the empirical laws for a certain class of neural networks? You will see that most of the time they're all going to be like a simplified versions of the real big neural networks. And the other one is also to provide some kind of intuition, like maybe introduce an algorithm that can be deployed in practice to infer a little bit more, like to study things that go a bit beyond the topology. So so that's the thing we're gonna talk about. So this is a picture from a recent paper by a student from Tom Goldstein's group that, well, of course, I mean, when you have to visualize a high-dimensional object, you're always a bit confused. It's always a bit confusing, right? So the question is, well, what can we, let's try to motivate and introduce some tools to help us, discriminate between that kind of two pictures, right? That probably people have in mind that this is what's happening in practice. So let's try to see what are so if we can say something a bit formal. So this is a problem, as also Sanjeev mentioned this morning, that is it's already I mean, many of the papers here I'm going to be citing are from, let's say, 4 years old, but for 4 years old in the scale of deep learning is very old, right? So it's in a sense, it's a topic that has been studied since a long time, and somehow the rhythm is accelerating in a nice exponential fashion, right? So there were some initial efforts that tried to get inspiration from statistical physics to build like these analogies, right? You basically try to come up with setups in statistical physics that kind of showed some qualitative structure, like at least at some qualitative level, have some similarities with what the neural network would see in terms of optimization. And then there's also some very nice works by Nadav Cohen and some of his collaborators that introduce these tools of tensor factorization and tensor analysis as another way to try to understand some of the non-convexity of the neural networks. And also, like some years ago, a couple of years ago, there were already some papers that tried to study things that are a bit more like closer to what we are going to do, more like topological in nature, and also like the different setups, right? So this couple of papers that concentrated on the empirical laws, on half-rectified networks, and as you see, like 2017, there's like even more and more papers, and I'm missing many of them, but just to show you that this is an area, a topic that is pretty active at this point. And so, first thing I want to convince you, I guess that I don't need to, I mean, this slide is probably not very necessary, but is that it's not because a function is non-convex that I cannot optimize it using gradient descent or like a local descent methods, right? So even in low dimension, it's very easy to construct examples of functions that are non-convex, but where there's absolutely no danger in running a local descent algorithm, right? And this is true in low dimension, very simple problems, and even more in practice. For example, if you think about a neural network, a deep neural network is not specified completely, right? That the way when I specify the neural network, there's a lot of ways I can rearrange the rows and the columns of the layers in such a way that they define exactly the same model, right? And this, in a sense, introduces symmetries in the parameter space that sometimes are discrete. Okay, so like, for example, the group of permutations is discrete. So what it means is that in practice, the landscapes that I will be facing have this flavor, right? They look at, maybe discrete copies of things. So this is non-convex, but there's no problem, right? I mean, there's no problem in that case of having a full local minima. And so, I hope that you're convinced that it's not because something is non-convex that it cannot be optimized. So how are we what is the tool that we're gonna use to try to understand a little bit what's happening? Is that we are gonna think about the loss surface in terms of its level sets, right? So just we consider a representation of the loss surface in terms of its level set. So basically this contains these sets that basically capture all the points in parameter space such that the loss is below a certain threshold. And so one thing that we are gonna be studying is like very simple topological properties of these sublevel sets. Okay, so for example, one thing that you could be interested is whether these level sets are connected or not. okay, for every energy level U. So in particular, if let's say that I have only one connected component for every energy level, any energy level U, why do I care about this property? So it's very easy to see that, of course, if there's only one connected component for every energy level, there cannot be any isolated poor local minima, right? Here I think about poor local minima in a strict sense. Okay, if you think about it, if there's a poor local minima, I can maybe surround it with a sublevel set, right? That is going to be separated from the rest. So this, you can think about this as a way to certify that there cannot be, so if I can construct examples where I can prove that this number of level sets is, the number of connected components is 1, then I'm kind of indirectly certifying that there's no poor local minima in the strict sense. And so more generally, it's very, again, by using the same argument about the symmetries of the network, it's kind of easy to see that in general, any neural network, it's never going to have an isolated poor local minima, right? Because for a given set of parameters, there's not only the discrete symmetries that are acting on these parameters, but most of the time, you also have continuous symmetry groups, right? For example, if you use a nonlinearity that is homogeneous, if you attenuate the layers, the parameters in one layer, and you multiply the weight of the other layer by the inverse, you get exactly the same model, right? So you can think that any point in parameter space has attached to it like a small manifold where the loss is exactly constant, right? So more general, we need to kind of generalize this notion of poor local minima, and one way to do it is to define what we call these valleys and spurious valleys, right? So a valley is just a connected component of a sublevel set. Okay, think about it. You take a level set, and then you just try to consider every one of the connected components as basically regions where the local descent algorithm can travel. And then a valley is going to be spurious if it does not contain a global minima. Okay, so in other words, if I have a spurious valley, there's a risk that if I do local optimization, I will get trapped, right? I'm not going to be able to travel to the globe, to the bottom. So a spurious valley, well, I mean, you could even use this analogy from, like the mountains and the lakes, right? So if I get trapped in a lake, I have a spurious valley. Okay, and so what is the maybe more actionable way to talk and to describe, to study this property is that, like an equivalent way to say it is that if I have a loss that has no spurious valley, what does it mean? It means that I can construct a path that starts at any point in parameter space, and I can move continuously from theta 0 to the bottom, right? To a point in parameter space that minimizes the loss. And I have to do it in a way that when I travel along this path, the loss cannot go up, right? The loss has to be non-increasing. Okay? So this, again, you can think there's a weaker property, right? Because here I'm asking that the loss to be non-increasing, right? So the loss, you could imagine that the loss has to travel some time where the loss is constant, right? And this, I mean, we don't have any algorithm right now that uses kind of gradient descent to do that, right? But you can think this is a kind of a weaker property that you should be able to satisfy if you want to converge to the bottom. So let's try to see if we can get some juice out of this property. So one way to start is to look at the models, deep neural networks, where we remove the nonlinearity, right? We just consider the problem where the activation function is just the identity. Okay, and so this is you can see this as a kind of a multi-linear regression problem where I can define here the loss in terms of its generic distribution. And so what do we know about this problem? So there's some results by using a critical point analysis that that tell us that this problem, despite being a non-convex and non-concave, has no poor local minima under certain conditions of the data distribution, right? So in the original paper, I think that the condition was a bit exotic, right? That you had to have a simple spectrum and full rank. Ever since, there has been some work by some colleagues, Teng Yuma, who was here, he's not here anymore. Well, Teng Yu did some updates and then follow-up papers. But again, there's still some conditions on the data. Okay, and so what we can say, in fact, is a bit stronger than that, right? Is that not only this problem has no poor local minima, but as long as the model is slightly over-parametrized, so basically if you consider here an arbitrary number of layers, and you make sure that the size of the hidden layer, a very hidden layer, is strictly larger than either the input or the output, then the loss is basically there's only one value, right? So basically the number of connected components is always 1 for every energy value. And this is also a result that extends to the case where we regularize, right? So in the case where we have 2 layers, this is the traditional multilinear regression. So even if you add the regularization in the form of ridge regression, the result still to be true. So here, again, it's a result that, in a sense, is weaker than the previous one, right? Because here we have to assume that the hidden layers, like the size of the hidden layer, have to be redundant. We have to basically pay redundancy because we have this property, right? But I mean, what we are showing is something that is, of course, stronger than lack of poor local minima. And in a sense, this is a result that is obviously kind of an artifact of the fact that there are no nonlinearities here, right? In the sense that if I have any architecture, any neural network architecture that has a nonlinearity, let's say a half rectification, like a RELU, then for any choice of architecture, you can find a data distribution where this property is false, right? So think about this as a kind of the adversarial game, right? So the user chooses an architecture, and then what I'm saying is that there's somewhere in the world a data distribution that generates a bad landscape. Whereas this is a completely universal property, right? The ones we had before, that has no assumption at all on the data distribution. So just to give you like a sketch of how this thing is proven, is as I said, the business is here to construct continuous paths where the loss behaves in a monotonic way, right? That's what we are. That's our game here. So the way it works is that of course, just sketching the idea is that we do an induction on the number of layers, and the idea that is going to be repeated again and again in this talk is to kind of lift the problem, so basically reparameterize the model in a way that we move into what we call the canonical parameters, right? So let's say that you have 2 layers, like a product of 2 matrices. So you can think about this model as basically a single layer model, right? Where I just identify the product of 2 matrices with a new matrix, W tilde. And so now I know that expressed in these parameters, the problem is completely convex, right? It's just, we are talking about least squares problem, right? So if the loss is convex, what it means is that it's very easy to construct such paths, right? We know that the linear path that connects 2 points in parameter space stays in the level set, because in a convex loss surface, the level sets are themselves convex, right? So in a sense, it's very easy to construct this path in this lifted parameter space. So then the rest of the proof is really say, okay, once I have this path in this lifted parameter space, how I factorize this path so that it stays in the actual parameters of the model. And so here we use like very basic properties of basically the topology of the space of invertible matrices. And as you know, the space of invertible matrices, you can think it as a manifold that has 2 connected components, right? Those that have positive determinant and those that have negative determinant. So that's why we need this slight overparameterization so that we can kind of move from one to the other, right? That's the only reason why we have this overparameterization. So one might wonder how much are we paying? How much price are we paying to impose this condition that, as we know, is stronger than we care about, right? Remember at the beginning, what we care is just having a path that goes to a global minimum, right? We don't really care that the global minimum themselves live in the same connected component, right? So the question is, how much are we paying to go for this condition that is stronger? So it turns out that, and again, this linear case is informative because it can really show us what are we losing here, right? And so one way to think about it is that, well, in this setup, in this linear case, I can construct like an equivalence class in parameter space, right? I can say that 2 sets of parameters are equivalent if I can relate each of these with a kind of a conjugate invertible, like a conjugate linear transform, right? I can reparameterize, I can interleave invertible matrices between every pair of things, and I know that because this thing is invertible, the loss is probably equal here and here, right? So in a sense, what we do is that we leverage this property to show that in that case, the multi-layer regression problem really has no spurious values, right? So you can always construct a path that continuously goes from any point to a global minimum. And here, there's really no assumption whatsoever on the data distribution, on the initial point, whatever. This is a completely general statement. And the way it works is essentially replicating the previous proof that I showed you, but now you have to work on the Grassmannian space of subspaces instead of matrices, right? You exploit this equivalence class, and you work on basically on the quotient space, and you do exactly the same proof as before. Okay, but this is still a linear case, right? And in a sense, what we are motivated is really understanding the optimization problem of like neural networks that are deployed in practice, which are of course non-linear. So in the process of going from the linear to the ReLU, we can stop in the middle and consider these kind of activation functions that are given by polynomials. In the case, just the quadratic case, right? And so, and here we introduce another idea that is going to be useful later. That is, well, if I have a nonlinearity that is nice, like a polynomial, I can linearize it quite easily. And how I linearize a quadratic nonlinearity, I just basically apply this, the outer product trick, and I can look at basically a square of linear combinations of x. I can see it as basically as a dot product between basically the outer product of x and some transformation of my parameters. So in other words, now I kind of disentangle, right? So here I express this activation function as something that looks linear with respect to this new variable that I introduced, right? And this is again like an algebraic manipulation that has been used again and again and again in like people who study phase retrieval, people who study inverse problems, and even semi-definite programs, right? So this is like a known thing. Okay, and so by using this analogy, we can automatically get a result that basically uses the linear case, okay? But now what we see is that because we have changed the input, right? We have made this step. We have essentially transformed an input that has, let's say, n dimension to an input that has dimension n squared. And so if we want to do this at every layer, what we see is that, well, the price that we need to pay to maintain this property has to increase in an ugly way with respect to the number of layers, right? But it turns out that we can actually be a bit smarter in that case and really exploit the geometry of semi-definite matrices to show that in that case, even like the size of the hidden layer, as soon as it's like essentially like a linear with respect to the number of inputs, you have no spurious values. Okay, and this result, in a sense, uses something that is very specific to the fact that you have this kind of representation in terms of like semi-definite matrices. And we believe that this is tight, right? So if m is like smaller than n, this result is false. There's distributions for which this thing is false, right? So basically, this result is essentially tight. Okay, and what about the ReLU? Okay, so here is like polynomials, and we'll see later how this thing can be extended to things that are like not quadratic, but just general polynomials. But one question is, well, what happens in the ReLU? So the ReLU, what we have as a result that in a sense is a bit weaker, and I will present it in just a second, right? So this is our setup. Again, it's like a one hidden layer network where now the activation function is a half rectification. And so what we showed with Daniel Freeman, like last ICLR, is that in that case, I cannot I cannot prove that there's no spurious values, but I can prove something that is a bit weaker, saying that for any 2 points in this parameter space that are in the same sublevel set, I can connect them with a path, right, that might have to go above the energy lambda, but the amount by which it has to increase the loss goes to 0 with the amount of overparameterization. Okay, so in other words, if I have a sufficiently large hidden layer, I have something that is like almost connected level sets, right? And the amount by which I have to disconnect, the energy by which I have to jump, goes to 0 with m. But of course, it goes to 0 in the ugliest way you could imagine, right? We really have this course of dimensionality, right? The rate at which it goes to 0 has the dimensionality of the input as an exponent, and this is bad, okay? And so, but in a sense, this course of dimensionality is really a consequence, and we will understand where it comes later in the talk. But it's really a consequence that we are, when you think about the kernel defined by the half rectification, if you want to basically embed this in a reproducing kernel, you need to have infinite number of dimensions, right? So basically, if you look at the functions generated by ReLU, you cannot approximate them, you cannot contain them in a space that has a finite dimensionality. Okay, so that's why we have this result here. Okay, so here's one possible way where you can now try to get all these examples that I described and see them in a more like a generic lens, right? And so what we are doing here is really trying to convexify the learning of basically the laws of neural networks, right? So if you give me a network like this, right, what we are really trying to do is to express, you know, like the functions that this network generates. So you can think this as a function of x, right? So this is just defining a functional space. So what we are trying to do is to write this functional space as a kind of a reproducing space, right? Where basically what we have is just when we move at this space, we can basically you know, you can really think about these functions as being linear functions, right, over some features of x, right? And so the idea is that now, if I look at this problem, right, in terms of these new parameters, that what I call these canonical parameters, now this is what's called a generalized linear model, right? And so the loss surface expressed in these parameters beta is completely trivial, right? It's a convex problem, and so I can connect these things. And so the goal of the game, it's really to show how can you actually go back and forth between these two kind of parameterizations. And so with this, so thanks to this analogy, we kind of have, so this is like kind of the main result of that we show is that when you can look at these you know, parameter, so if you can actually embed this reproducing, like this reproducing function, this functional space in a way that it has finite dimension, right? So this is now, we call this the intrinsic dimension of the model. If the size of the hidden layer is at least the size of this reproducing space, then this loss has no spurious value. Okay? So, and in particular, this generalizes the things we said about the quadratic case, and of course the things that we said in the linear case, right? Because in the linear case, there's really, I mean, this space. I mean, this is by definition the linear representation, and it also includes the empirical risk minimization, right? So if now you take a continuous activation function, for example, like the RELU, if you want to understand the empirical loss, the space when you evaluate this thing, the empirical loss has dimension that is determined by the number of data points. Okay, so in that case, we show that you can use this result to show that in that case the empirical loss has no spurious value. And there's a number of works that are trying to build on trying to construct these reproducing kernel spaces out of deep neural networks and convolutional neural networks. I recommend that you look at this recent paper by Julien Méral and some of his student. And then there's a very nice paper by Francis Beck also on using basically these convexified neural networks and doing some learning theory. And so there's yet another kind of geometric way where you can also interpret what we are doing. As I said, is really to think in terms of this functional space, right? So if I can look at my model as basically defining you know, a space of functions that go from the input space to the output space that is parametrized by some network parameters, right? But I can just look at it as a space of functions. And if I just doing regression, right, I'm essentially solving problems that look at this, right? So I basically need to minimize the distance from, you know, from a target output that is like basically just estimating the conditional mean, and I can move in this functional space, trying to minimize basically a norm that is basically an L2 norm that is defined by some data distribution, right? So you can think this is a kind of a Euclidean space, and so what we have seen so far is essentially that whenever I can guarantee that this functional space is convex, essentially that's the result we are using to prove that there's no spurious value. But this is not necessary, right? So there are examples, as I said before. For example, if you use like linear networks that have in the arbitrary sizes of the hidden layer, this defines a functional space that is non-convex, right? The space of matrices of rank 1 is non-convex. But still, I can prove this property that it has no spurious value. So a more like a necessary condition is something that still has to be given a name. I don't know, the name I chose so far is this notion of ball connected, right? It's a space that when I intersect it with balls, the intersection has only one connected component, right? And so if you think about the convexity, it's the intersection with lines, right? So here, intersecting with balls is a bit more general. Anyway, so this is just to give you this kind of a more geometric view and more intrinsic view. And so another question is, well, what happens when the model is not sufficiently over-parametrized, right? So I told you that whenever you have put enough parameters in the hidden layer, then you can certify that there are no spurious values. So what happens when the network doesn't have enough parameters? So so here we can kind of hypothesize, postulate that there might be, of course, maybe the property is not going to be verified anymore, but the question is, well, in what way the property degrades? And one possible motivation, and something that we are currently exploring, is this notion of energy barrier. Okay, so this energy barrier is something that is originated in the community of statistical physics, and it relates to some properties of functions like this. There's like what they call like glassy systems, like for example like a spin glass. So you construct this Hamiltonian of these systems, and you can see this Hamiltonian as basically a Gaussian polynomial over the sphere. And so if you look at the loss surface of this polynomial, you see that it has a bunch of critical points, right, all over the place, but there's a very nice way to organize these critical points depending on which energy they emerge. And what they show is there's this very nice phenomena that there's a notion of energy barrier below which, so basically above this energy barrier, the probability of finding a poor local minima is vanishingly small, right? So what it means is that in practice, when you try to optimize these polynomials, with high probability, you always end up with this energy barrier, right? That is, of course, in general, is not equal to the global minimum, right? It's like above the global minima, but it basically contains all the, so above this energy barrier, there's no poor local minimum. And so the question is, well, whether we can have the same kind of phenomena in our setting, right? This idea that if I have enough parameters, then any path I can find any path that connects from any point to the global. So what happens if I don't have enough parameters? Maybe I can still go construct good paths that might not go to the bottom, but might get sufficiently close. So this is the idea that we are trying to basically to advance. And so the one way where you can quantify it is to define this kind of energy barrier, right? That it's a function of two things now. It depends on the input dimensionality n, and on the number of parameters that I give, like the number of parameters of the hidden layer. And so if so what I know is that if I make m sufficiently large, this thing matches the global minimum, right? But if I have a smaller number of m, this thing is going to be large, right? And the idea, so the way where you can interpret this result is saying, well, what would be the best loss if before trying to optimize this landscape, I'm allowed to just slice the input data into a subspace that has appropriate dimensionality, right? So think about this as a way to think about this energy barrier. And so what we are conjecturing and what we are working on proving is that in general, like this is a general result, that the loss surface, defined like this, has no poor local minima, so basically has no spurious valley above this energy barrier beta, of course. And when m matches the intrinsic dimension, this quantity matches the global minimum. Okay, so now I hopefully gave you like a bit overview of the kind of the analytical results that we have. We also want to study. We might also want to study what happens in practice, right? So more generally, one thing that we would be interesting is also how this descent path that the actual gradient, this stochastic gradient descent will follow. What kind of conditioning? So in other words, how far do they need to travel in regions where the curvature might be very small? Okay, so in other words, here we have two level sets. Both are connected, but you might agree with me that maybe optimizing over level sets that look like that might be better for SGD than optimizing over these level sets, right? And the reason for that is that, well, if I need to move from, let's say, this point to something that is in the middle, I might have to travel a lot, right? I might have to do a lot of movement over regions in parameter space where the loss does not change. And so one thing that we try to do is to estimate basically the curvature, like how basically the regularity of these level sets by trying to estimate geodesics that of the sublevel sets, right? So the way what we're going to do is try to find, like, given 2 points in the boundary of the level set, we are going to try to find a path that goes from one to the other in such a way that it stays in the level set, right? And we are going to try to make this path as short as possible. So making a path that is as short as possible is a geodesic. And so how can you do this in practice? So what kind of algorithm can you do to do that? Is that, well, the quantity that we need to find is that given these 2 points, right, that are in the level set, what we need to find is the shortest possible path that stays in the level set. So how do? We start by looking, okay, maybe the best thing that we could hope for is to do a linear path, right? So that's the first thing to do, is we try to see if the linear path is in the level set. If that's the case, we are done, right? That's the shortest path. If it's not, we might need to perturb this path, right? So we start from here and we try to move this point until it falls into the level set again, right? And we penalize how far we move from here. And once we have found this point, we just iterate the same thing in a dynamic programming approach, right? We just do the same thing from here to here, et cetera, et cetera, et cetera. Okay? And so with this, what it gives us is now a measure that is kind of intrinsic, right? So now what we can try to see is what is the length of this path relative to the Euclidean distance, right? So in other words, that if you see in the y-axis something that is close to 1, what it means is that the path is essentially linear, is like a straight line, right? So if the problem was convex, you would have, in this curve would always be 1, right? And so here what we show is that for real problems with real networks, we estimate this thing, right? So on the x-axis, you see the energy level, and on the y-axis, you see this normalized length, right? The normalized path. And so what you see, maybe not surprisingly, is that, for example, MNIST is a problem that is essentially convex, right? So basically, when you train a neural network on MNIST, what the training algorithm sees are level sets that are essentially convex, right? So up until basically the lowest error that you can make on the test set, right? So basically, if you look at this path at the bottom of the energy of the lost surface, you need to bend the path by basically 7%, right? Almost very, very little. So if you do this on more complicated data, you see that basically for large energy levels, this is completely convex, but then it starts to get a little bit more non-convex. And even for problems that involve, let's say, text modeling, language modeling, we get exactly the same phenomena. So here, what is surprising or kind of interesting is that whereas in the theory side, we are able to show that the level sets are connected or that there's no spurious valley under kind of heavy assumptions, right? A two-layer network, sufficiently over-parametrized. What we see in practice is much more brutal, right? We have never found an example that we used where 2 models are disconnected, right? So we have always been able to connect any 2 models in a way that the loss does not increase. Okay, so we have not, of course we haven't tried very much to find for this disconnection other than in synthetic examples, but what this seems to suggest is that there's still a lot of room to make these things, to explain what happens in practice. And so, so just as a conclusion, right, with what we are now interested in advancing is like trying to understand whether it's true or not that there's this energy barrier, right? So what happens when the assumptions of over-parameterization break? Do we have an energy barrier or not? And this is important because, of course, if you have an activation function that is generic, right, you might want to decompose this activation function into maybe like the smooth part where we can use our theory and the error, right, and the residual. And so if we have some form of like a stability with respect to this error, we can maybe hope to, basically say things for a much larger class of activation functions, right? Maybe, eventually by having to increase this energy barrier. And so, I think with that, I would like to thank the organizers. And here are like the 2 references that basically cover all the results that I presented today. Thank you.
So we open the questions from the audience.
Given the high dimensional space for a lot of this data, is it expected that the deformations of the path from the non-convex to the these convex geodesics, is it expected that they should be not too much off from one?
Well, not in general, right? I mean, they have to be in the level set.
Mm-hmm.
So, I mean, what we show, I mean, clearly this property depends on the, like, for example, how deep you are in the energy level. So if you have a model that does super bad, there are a lot of chances that there are many models in the neighborhood that will do equally bad, right? So it's very easy to move. But as you get better and better test error, you might expect that maybe, you know, the perturbations that you can do to the model so that it stays in the level set are much more reduced. And, you know, and basically this idea of geodesic is a global property, right? It's not just a local property of local perturbation. So yeah, I mean, maybe after the fact, you can argue that, yeah, this is again another consequence of the high dimensionality. But for example, like actually proving that, you know, we can bound these geodesics, I think this would be interesting to formalize. Yeah.
How you compute those geodesics? Do you
1 minute.
Could you say how you compute those geodesics? Do you randomly splat down points and?
Yeah, so the algorithm goes as follows. It's like a dynamic programming approach. So
these are just 2 example points. So
these are two models, so 2 points in parameter space that have the same loss. Okay, so they're in the boundary of the sublevel set. And now what I will try to do is I will try to find a third model that is as close as possible from being in the midpoint. But the constraint is that the loss of this third point has to be in the level set.
Sure, I got that. I thought you wanted to measure the geodesics within that whole level set, though, not just for one particular
you
path.
estimate. So basically
Yeah.
what you do is then you sample like a number of different arbitrary pairs of models, and then the result that we show is the report is the average.
So you randomly splat those down. How do you find points in the level set to begin with, I guess?
So yeah, the finding point in the level set is just you initialize SGD from some random initialization, and then you run it until you are happy with the loss. And then this guarantees that you are in the boundary of the level set.
So again, with those theta 1s and theta 2s, have you tried creating kind of theta 1s that don't come from SGD but have the same loss? I'm thinking run SGD, then like compress prune or something, and then you get something that looks very different, something that could come from SGD but somehow has the same loss, and then you could try this again.
Yeah, this is a very good question. So what we tried is, for example, like one model from SGD and one model from GD, and then connect, and that still worked. But I've been asked this question whether you could do this adversarially. So, and I believe that the answer might be very surprising, that you could adversarially look for points in parameter space that are, you know, hopefully disconnected from anything else. I don't have any principal algorithm for doing that, but I think it's a very interesting project. I don't know, yeah.
Do you have any other questions? No?
Could you say more about how you kernelize a deep network? It's not obvious how. Is there a
Yes.
simple intuition you can give?
So the intuition is really, in our case, let me just say that we are focusing on just a 2-layer network, so just one hidden layer. And in that case, it's really, this is not me. This is me? Ah, okay. So yeah, so in that case, where is it? It's here. Yeah. Well, so here, think about you can think this as essentially maybe actually I can write it. I'll write it here. The idea is that now you can think about this. Right, for every W, for every parameter in my first layer, I have a function, right? That this is a function. So now the question is, I take the ensemble, the family of these functions for all possible values of W, and I call this my functional space. So the question is whether you can actually write this functional space as a reproducing kernel space. Okay, so this, of course, you can only do it for certain classes of activation. So if, for example, if you use a polynomial, then we have an explicit construction for that. But you are completely right. There's no general recipe for doing this for general activation functions. But if you're interested in this, there's like some references there that really do this for deep networks. So that's, yeah.
Okay. Any other questions? No? Okay.
Thanks. So in this case, even if you have a kernel mapping, then the result is that there will be a path if the number of hidden layers is higher than the dimension. But typically these dimensions are very, very high, right?
Correct, yes. So either so if you want to have something that is true at the population level, so for infinite number of data points if you want, then you need to rely on the smoothness of the activation function to get like this finite intrinsic dimension. Otherwise, as we discussed, you can get this finite number by reducing the number of data points. And of course, there's all these combinations in the two. But you're totally right. For general activation functions where this is like an infinite dimensional space, and if you have a finite number of neurons, we don't have any universal method to prove that there's no pure local minima.
But this is without assuming anything on the mapping from parameters theta to that linear classifier in the feature space, A
Yes.
theta.
Yes.
Is there any result you're aware of that relies on some structure?
So
of
for
that
example,
mapping?
the result we have on the quadratic case is really much better. So that we have this kind of master theorem, right? That is this one, that uses this as a bound. So if you look at this at the quadratic case, what you see is that you would have like n squared here. And what we show is that, so if you apply this theorem for the quadratic activation, you would say that if the number of neurons is larger than n squared.
Is that because Q is equal to n squared,
Yes.
or because M can be smaller?
Because that would be, Q here would be n squared in the case of quadratic nonlinearity. But what we have is that the result is true for M, like of the order of n.
That's an empirical result?
No,
Or-
it's a
oh.
here. So what it means, you're right. So this general construction that we have is it's too general, right? In a sense, it doesn't exploit. So here, the way it works, we can discuss offline if you are interested. But the way you construct these paths, there are essentially two ways to move from parameter to parameter. One is using what's called like a mixture. So think of that you kind of do like a linear, you just move continuously. You attenuate one set and you activate the other one. And the other one is more like a transport, right? You can think about moving parameters in two ways, right? Either as a mixture or as a transport. So it turns out that this result that we have, the general result, just uses mixtures, right? So if using mixture, it's a bit more sloppy than if you know how to construct things that actually transport, you can typically do better. You could get tighter bounds. So you're right. For general things, you could always hope to do better by kind of exploiting a lot the geometry of basically this kernelized space.
Okay, thanks. Take it offline.
Any final questions? Okay, we thank the speaker, Joan, and we move to the next speaker, Andrew. Thank you, Joan.